particular to understand ADS4 vacua, and in order to do that, you would need to understand various conformal field theories if you want to have the dual description of those ADS4 vacua. Also, these various field theories might be useful for condensed matter applications. Now, the theory we will be discussing is a particular gauge theory, which has a UN cross UN gauge group. And we have, in addition, matter fields, which are in the bifundamental representation. So we'll have 4 fields, 4 complex fields in the n bar representation of this gauge group, and their corresponding fermionic partners, 4 fermionic partners. And then, of course, we have the complex conjugate fields. And we have also these gauge fields. So that's the field content of the theory. The Lagrangian contains like a Chern Simons Lagrangian for the 2 gauge fields with opposite levels for the 2 gauge groups. So this is the first group and this is the second group. Then it has a kinetic term for the matter fields, but it has no kinetic term for the gauge fields. So, and in addition, we have some Yukawa couplings for the fermions and then some potential for the scalars. So all the terms in the Lagrangian are scale invariant. Of course, the Chern Simons term is even topological, but the rest of the terms are all scale invariant. So the C field, for example, has a scalar field has dimension 1/2 in 3 dimensions. So C to the 6 is the scale invariant form of a potential in 3 dimensions. The theory has an SO6 or SU4 symmetry, and it will have 6 supercharges, which transform in the vector representation of SO6. In addition, we'll have a U1, we call it U1 baryon global symmetry, and it's related to changing the phase of all these scalars. It's essentially that, except for a minor thing, which is that this symmetry is actually gauged, and however, there is a second conserved U1 current, which is given by the trace of the gauge theory fluxes. So this involves only the U1 parts of the gauge group. And there is a constraint, a Gauss law, that says that these 2 currents are 0. And so then the conserved charges are essentially given by the integrals of this quantity, which through this equation are related to conserved charges we would have had if this had been a global conserved symmetry. This phenomenon will probably be explained a little more by other speakers. Now here, let me just explain in this transparency why this theory has n equal to 6 supersymmetry. So in 3 dimensions, you can write without too much trouble theories that contain Chern Simons terms and have n equal to 3 supersymmetry. So 3 supercharges in the counting of 3 dimensions. And this you can do for general matter content and general gauge groups. And then the Lagrangian is essentially completely fixed. And in some special cases, you can write n equal to 4 theories, but there you require some special gauge groups and some special matter content. Now, the theory we are considering can be written in n equal to 2 notation. So n equal to 2 in 3 dimensions is the same amount of supersymmetry as n equal to 1 in 4 dimensions. So we can use the superspace essentially of the 4-dimensional theory reduced to 3 dimensions. And we can have chiral superfields. And so instead of the 4 bosonic fields we were considering, we can consider 4 chiral superfields, which are denoted by A and B. So these have 2 indices, A1 and A2, B1 and B2. And the superpotential is the same as the superpotential in the Klebanov-Witten theory. So this theory is closely connected to the Klebanov-Witten theory. And notice that a quartic superpotential in 3 dimensions is also naturally marginal. So in the Klebanov-Witten theory, it was hard to, well, one had to consider a strongly interacting theory in order for this superpotential to be marginal. But in 3 dimensions, this superpotential is naturally marginal. So we can have a weakly coupled theory with this superpotential, and it will be scale invariant. Now, when we choose this n equal to 2 notation, we break the SO3R symmetry that an n equal to 3 theory has. And in addition, we see that the superpotential has an SU2 cross SU2 global symmetry. And we find that this SU2 cross SU2 global symmetry does not commute with the SO3R symmetry of the n equal to 3 theory. What that implies is that by commuting these generators, acting first with this generator and then with these ones, we generate new symmetries, and we form a whole group, which is an SU4 group. So you can think about this a little more, and you find that you get an SU4 symmetry group. So by this simple argument, you find that the symmetry of the theory, the R symmetry, should be SU4, SO6, and there should be 6 supercharges in particular. And you can, the C fields that I described before are related to these chiral superfields by this relationship. So we have A1, A2, B1 star, and B2 star. So, and in these papers, the explicit supersymmetry and R symmetry that I mentioned here was checked. And in this last paper, the general theories with n equal to 6 supersymmetries were written down. I mean, you essentially have these theories plus the addition of extra U1 factors. Oh, what happened? Okay, now I like to relate these theories to M2 branes. And in order to do that, I'll first sketch this in this transparency, what we're going to do. So we're going to start with a brane construction of an n equal to 3 UN cross UN Yang-Mills Chern Simons theory with the same matter fields. So the difference with the previous theory is that now we'll add a kinetic term for the Yang-Mills fields, and therefore we have a whole Yang-Mills multiplet. And then we'll relate this by some U dualities to M2 branes probing a particular 8-dimensional manifold. And the 8-dimensional manifold will be a smooth manifold except for a point where there will be an R8 cross CK singularity. K was the level of the Chern Simons term. And we'll see that when we go to the infrared, the M2 branes will be probing that R8 mod CK singularity. So let's discuss this in a little more detail. So we start first with an n equal to 4 super Yang-Mills theory with a bifundamental hypermultiplet. So this amount of supersymmetry is the same as n equal to 2 in 4 dimensions. And you can engineer that by taking 2 parallel NS5 branes that are sitting on a circle, and on that same circle we put n D3 branes. So the D3 branes are broken into 2 pieces, so each piece gives rise to a UN factor. Now then we take this one of these 5 branes and we rotate it in the 3 transverse dimensions, and we also add k units of the 5 brane charge, and these k units of the 5 brane charge induce are responsible for the Chern Simons term, and then the rotation will give some masses to all the other fields in the Yang-Mills multiplet. So this theory has a Yang-Mills vector multiplet, and which will contain 4 states. One will be the gauge field, which gets a mass due to the Chern Simons term, and the rotation gives a mass to all the other fields in the Yang-Mills multiplet. So at this level, we have an n equal to 3 Yang-Mills Chern Simons theory, and all the fields in the Yang-Mills multiplet are massive. Okay. Now then, we take this configuration and we do a T-duality along this circle, and then we go to type 2A theory, and after that we leave to M theory. And what happens is, after you do these 2 steps, the 5 branes become Kaluza-Klein monopoles in M theory. So it's easy to see here, for example, for this brane, we T-dualize, that becomes a Kaluza-Klein monopole, and then we lift, it continues to be a Kaluza-Klein monopole. And for this one, it's the same argument, but it's a little more complicated. So in the end, in M theory, we have 2 circles. One was the T-dual of this circle, and the other one is the 11th dimensional circle. And then we can have Kaluza-Klein monopoles associated to any linear combination of these circles. And so these 2 Kaluza-Klein monopoles are associated to 2 different circles in the M theory picture. And they form a space which is called toric hyperkähler manifolds that were studied they were introduced in the physics context in this paper, where they were precisely related to these systems of intersecting 5 branes. And so that space is completely non-singular, where the monopoles are not intersecting, because a single KK monopole is a non-singular space. But then they intersect at a point, and where they intersect, you can argue that you get an R8 mod CK singularity. I mean, these spaces are very explicit. You can write the metric completely explicitly. They are very similar to the Gibbons-Hawking metrics, where you can explicitly write the metric. So it's not anything very mysterious. And you can explicitly check that you get the singularity at the tip. So at the singularity, so if you look just close to the singularity, the R symmetry and the supersymmetry is enhanced to n equal to 6. And similarly, in the field theory case, we can integrate out all those massive vector multiplet fields, and we end up with a theory which contains whose only dynamical fields would be the matter fields, and will be the conformal Chern Simons matter theory that we discussed in the very beginning. So what we have done here is we related this quantum field theory to the theory living on M2 branes sitting at this singularity. Now let me here mention a couple of features of this theory. So the first is that this theory has a coupling constant, which is 1 over k. So the theory becomes free in the large k limit. And now notice that one of the early objections to this program of trying to construct Lagrangians for M2 branes was the idea that if you could actually write a Lagrangian, then no one can forbid you from multiplying the Lagrangian by a number and then have a whole set of theories, where you can vary the coupling. Now, here you don't have a marginal parameter because the Lagrangian is only gauge invariant up to factors of 2 pi. So that number is restricted to be an integer, but still you can multiply the whole Lagrangian by a number and you expect to find the sequence of theories, and that's indeed what one finds here. There is a whole sequence of theories that depend on this parameter k, and you can go to weak coupling. Now, another interesting fact is that we can take the n going to infinity limit, and we can keep the Toft coupling fixed. So this theory has a Toft coupling limit, and the Toft coupling becomes a continuous parameter. So even though the coupling k is a discrete parameter, once you go to the Toft limit, you have a continuous parameter that you can vary. Now you can analyze the field theory moduli space, and you get what you want. I think probably Sunil will talk a bit more in detail about this problem, and which is the same as the field theory, as the moduli space for M2 branes probing the singularity. Now for k equal to 1 and 2, based on the moduli space, we expect the theory to be SO8 invariant, and we expect the theory to have n equal to 8 supersymmetry. And we'll discuss a little later a slightly better argument to see this fact. Of course, at k equal to 1 and 2, the theory is strongly coupled, so we can't trust directly the Lagrangian. For n equal to 2, so in the case that we have rank 2 and we change the group from U2 to SU2, so we consider a slight variation of the theory, which is SU2 cross SU2 theory, then you can explicitly see that the theory has n equal 8 supersymmetry for any value of k. So even at weak coupling, the theory will have n equal 8 supersymmetry, and of course it's the Bagger-Lambert-Gustafsson theory that was constructed before our work. So. Now, you can also look at the gravity dual of these theories, and well, we know the gravity dual for M2 branes. We just make a quotient by CK, and so we get that simply this simple space. So that's the gravity dual of the theories we're talking about. If we take the limit that k is large, we can reduce to type 2a. So when k is large, there is a circle on the S7 that is becoming very small. This CK quotient acts without fixed points on S7, so this is a completely non-singular space. And when you take k large, you get, again, a completely non-singular space, which is ADS4 cross CP3. And this type of solutions were considered in the past by Nielsen and Pope. And they have n units of flux on ADS4 or dual flux over the CP3, and k units of flux of the two-form field strength on a CP1 through a CP1 inside CP3. So this is a particular solution of the solutions that Alessandro Tomasiello was describing this morning. Now the radius of curvature of the ADS4 and the CP3 and the CP1 inside CP3, so all the radius of curvature, there is a unique parameter here, a unique radius of curvature, and it's given by the Toft coupling, the square root of the Toft coupling in the field theory, which is this ratio of n and k. So we see that in the Toft coupling, when n goes to infinity, we get a finite value for the radius, and so we get a weakly coupled string theory. Well, I didn't write here the expression for the dilaton, but the dilaton is also fixed in terms of n and k, and when n goes to infinity, so in the 't Hooft limit, the dilaton goes to 0. Now we can vary the 't Hooft coupling between the perturbative gauge theory regime and the gravity regime. So we can vary it continuously, and we expect that in the 't Hooft coupling, many quantities should have a continuous interpolation between the free field theory result and the gravity regime. Now, using the gravity dual, we can compute the thermal free energy at high temperature, at any temperature, since it's a conformal theory, but we can compute the free energy for high couplings, for high values of lambda, and what we find is, the famous 3/2. So that's the same 3/2 that was originally seen for the M2 branes. So all that I would like to point out here is that this factor of 3/2 in this type 2a description, or in the 't Hooft coupling limit, becomes an n squared times lambda to the 1/2. This is just a very simple rewriting of this formula. And so what we see is that we get the factor of n squared that we expect, and we here get some function of the coupling, which is analogous to the factor of 3/4 that we get for n equal to 4 super Young mills. So at weak coupling, here we expect, we actually can compute here that we have a number of order 1, and then that number of order 1, when we go to large coupling, should become a 1 over square root of lambda, and we should, this is what we explicitly see from the gravity solution, but of course it would be very nice to have a field theory explanation for that fact. I'm not saying we have a field theory explanation, but the 3/2 translate into this particular dependence on lambda, and you can try to, in principle, study it in the 't Hooft coupling. You could try to find an argument for it in the 't Hooft regime. Now let me mention a few facts about the spectrum of operators. So there are some operators which you can write down very simply, which consist of a sequence of C fields and C star fields. So the C field is the matter fields are in the bifundamental representation. So in order to make a gauge invariant combination, you have to combine the field with its adjoint and so on. You have to form chains of this kind. Now in n equal to 1 notation, these become these operators of the form A and B, etc. Well, you can find these operators, these chiral operators are a particular subset of these general operators. And some of these operators, so if you contract all these indices symmetrically, are BPS, and you can compute their dimensions and should correspond to certain gravity modes and so on. But in addition to these operators, we have other operators in this theory, which are so-called 't Hooft operators. Now these are operators which you cannot write in terms of the fundamental field of the Lagrangians, but rather you write the way you construct them is by changing the boundary conditions of the path integral at the point. So you select the point where the operator will be inserted, and you say that there will be 1 unit of magnetic flux on this 2 sphere. So that's how the 't Hooft operators are constructed, and of course we in general can have these operators. Now one new aspect that happens in this theory is that if we put 1 unit of magnetic flux, the Chern Simons coupling implies that that flux will carry a certain gauge theory charge, and will transform non-trivially under the gauge group. And so you also have to insert, in order to make it gauge invariant, you have to insert some fields, some of the bifundamental fields that we talked about before. So in the end, you get operators which contain these fluxes on the S2. So I denote this by the letter T means the 't Hooft operator with, let's say, 1 minimal unit of flux, and it has to be accompanied by the insertion of K of these fields. And so these operators carry this global charge that I mentioned in the very beginning, and are some other operators of the theory. Such operators were analyzed in a series of papers by these authors. So these two kinds of operators correspond to different kinds of states in the gravity dual. So for example, in 11 dimensions, these operators correspond to Kaluza-Klein modes. So the BPS operators of this kind correspond to Kaluza-Klein modes with no momentum along the 11th direction, so along the circle on which the CK quotient is acting. And they correspond to ordinary string states in the type 2a description. While these other operators correspond to modes with momentum in the 11th direction. And when you reduce to type 2a, of course, they would correspond to D0 branes, to D0 branes. So in the Toft limit, they become very heavy, but, well, in principle, if k is small, they could also be light. So in the particular cases of k equal to 1 and 2, the theory is supposed to have extra symmetries. And one can, in fact, argue that we have these extra symmetries by looking at the currents. So instead of looking directly at the current, we look at the scalar field in the current supermultiplet that is made out of two scalars. So for example, if we take an operator which is made out of a C and a C, well, we take the field C and then its complex conjugate. So such an operator is the scalar, this is a scalar operator, and it's in the same supermultiplet as the ordinary SU4 currents. By the ordinary SU4 currents are the SU4 currents, which are the R symmetry that we can see explicitly in the gauge theory, in the weakly coupled description. We see them explicitly in the Lagrangian. In addition to these operators, we can construct for k equal to 1 and 2, we have two Toft operators, either with 2 units of flux or 1 unit of flux, and contracted with 2 C fields. And such, so there will be BPS operators of the dimension 2, that's the dimension of these 2 C fields. And since they have dimension 2, so the current will have dimension 3 and it will be a conserved current. So in this way, you can see that you have these conserved currents. Of course, this argument relies on the fact that the dimension of this operator is the naive dimension, so the dimension a half that we can just compute by looking at the C fields. In addition, for k equal to 1, we can construct this type of operator, so the Toft operator with 1 unit of flux times the C field. And this, again, is a dimension a half field, and that should be a free field and should represent the center of mass motion of the branes. Now, this fact that for special values of k we have extra symmetries is a fact that is familiar from other theories. So, for example, if we take a compact boson in 2 dimensions, so the compact boson in 2 dimensions has a parameter which is the radius of the boson. And in general, it only has U1 cross U1 symmetry, but at a special value of the radius, the symmetry is enhanced to an SU2 symmetry. And so here is something similar. We have enhanced symmetry for particular values of the level, of the Chern Simons level. Now, an interesting aspect of this story is the fact that this string theory on this background, and similarly the gauge theory, appears to share many similarities with ADS5 cross S5. And in particular, this theory is classically integrable, so you would like to understand whether you can repeat the whole program that was done for ADS5 cross S5 and repeat it for this case and find another example of an integrable string theory or an integrable gauge theory, string theory duality. And indeed, many of the steps were repeated. And so, for example, in the paper by Minamhan and Sarembo, they looked at the weak coupling spin chain, and they found that it was integrable in the relevant sectors. And then you can try to reproduce the whole story with choosing this vacuum and then finding impurities on this vacuum. So in this case, the corresponding vacuum would be a vacuum made of the fields A and B1, so a whole sequence of those. The unbroken symmetry by this vacuum in that case was SU2 cross SU2 squared. In this case, it's SU2 cross U1. So it's a rather similar story. This SU2 cross SU2 can be used to determine the dispersion relation, and we have a similar story. Now here, the coefficient here will be a function of lambda, and so on. Well, and there were many aspects that were explored. And there's even a conjectured exact phase for this problem, but there still hasn't been enough checks to know whether this is correct or not. So, but well, this is a field that is developing, and probably in not too long we'll know what the correct answer is, whether it's integrable or not, and what's the precise solution. Now there are various generalizations you can make for this story. So one is a simple one is to change the ranks of these two gauge groups. And in the M-theory description, that corresponds to discrete Wilson lines of the C field. or torsion F4 flux. So it's like taking the same singularity and adding some torsion F4 flux, or what is the same thing, adding these discrete Wilson lines for the C field. And one interesting aspect of these theories is that if n minus m is bigger than k, then we don't have any candidate torsion here, because this only takes k values. And the conjecture is that these theories don't exist if n minus m is bigger than k. So even though you can naively write a Lagrangian, the idea is that you can never define that Lagrangian. Well, first of all, that Lagrangian in this regime will always be strongly coupled, and the idea is that you cannot find it as the infrared limit of any other well-defined theory. And then there are similar things you can do with orientifolds and so on. Okay. Now you can change the theory in various ways. So one thing you can do is you can add a mass deformation, and then the theory has lots of different vacua where the M2 branes grow to M5 branes. And when you count these vacua classically, you run into some puzzles, but nobody did yet the correct quantum calculation for the number of vacua, so there is a problem to be solved. You can also find the solutions describing M2 branes ending on M5 branes, which originally were thought about by Basu and Harvey, and were one of the motivations for trying to find this Lagrangian for M2 branes. So in this case, you can find them explicitly. So you can consider more general quivers, and some of that was described by Tomasiello. And you can also squash the S7, and this preserves only n equal to 1 supersymmetry, and there is a conjecture field theory. Another thing you can do is you can consider flows that that deform the S7, that breaks the SU4 symmetry to SU3 symmetry. And one interesting aspect of this flow is that you have to add to the Lagrangian a Toft operator. So we're adding one of these Toft operators to the Lagrangian. So you can also consider some non-supersymmetric examples and so on. So in conclusions, we presented an n equal to 6 conformal Chern Simons matter theory that has a discrete parameter k that allows us to go to weak coupling. And so the Lagrangian becomes trustworthy. Well, yeah, the coupling multiplies the whole overall Lagrangian, and so the fact that we can go to weak coupling ensures that this Lagrangian description is weakly coupling. Well, it's good in some region. At strong coupling, for k equal to 1 and 2, the theory has an enhanced symmetry, and there is an interesting Toft limit and possibly integrable. So that's still yet to be confirmed, but there is an interesting area of research in that direction. Now in the future, one thing one would like to do is understand better these Toft operators, and in particular develop techniques for seeing and exploiting the appearance of symmetries at strong coupling, how we deal with these Toft operators when we put them to the Lagrangian, what are efficient rules for dealing with this story, and so on. One would like to answer this question of integrability. Of course, one would like to understand more general ADS4 vacua, and as I said, there were many examples, but which were similar to the examples that were found for ADS5. But for ADS4, we also would like to find the vacua, the ADS4 vacua that have a large separation between the radius of the internal space and the radius of ADS. Those are relevant for describing very big ADS4 spaces. And maybe, well, even if presumably the data of the LHC might be described by one of these 3D CFTs, but well, even if we can't describe the universe, perhaps we can find some interesting condensed matter applications for these theories. Well, thank you very much.
Do you have time for some questions?